Okay, welcome to the problem solving portion of the video. My webcam is acting up a little bit, but the audio should be okay and the document camera seems fine. So first thing I'm going to do with you guys today is go over a little bit of the math, like the equations behind ionization energy, photoelectric effect, PES, etc. So you can find this equation right here in the book. What this essentially says is that the kinetic energy of an electron is equal to, first of all, this equation right here. Those of you that are in physics may recognize this. This is 1/2 times the mass times the velocity squared. That's the kinetic energy of any object, okay? So the kinetic energy of an electron is equal to that, but it's also equal to, okay, and this is important, the energy of the photon used to release the electron minus the energy required to ionize the electron. Okay? So the energy required to ionize the electron, that's that minimum value we were talking about before, right? So that's the minimum amount of energy needed to release an electron from an atom. Okay, that's what this term means right here. This term is the total amount of energy used by the photons. So the photons are what get shot at the atom, and you take that value, you subtract that by the amount that's needed to get it out of the atom in the first place, and what you're left with is the energy of the electron, or the kinetic energy of the electron. Okay, this right here is measured by a photoelectron spectrometer machine, okay? Along with the energy of the photon that's used. Okay, so like you can set the amount of energy you want to use in those photons that get shot at the substance. If you subtract those, okay, so if you just sort of ignore this factor here, you take that equation and you rearrange it a little bit, you can solve for this term, okay, which is right here. Okay, the energy of the electrons that are emitted is equal to the difference between the energy of the photons used and their kinetic energy. Okay, so what does that mean when we look at a photoelectron spectra or a spectrum? Okay, well, let me talk about that for just a minute before I actually get to the problem that we're going to do with this. What that means is that for this electron or electrons right here, this energy value, okay, which is, I don't know, somewhere about like 0.8 megajoules per mole, that's being calculated by the photoelectron spectrometer. They're taking the electrons or the energy of the photons being shot minus the kinetic energy of the electron, which they're detecting, and they're just spitting out this value. Okay, and so that's how that device comes up with the values for these different, and like where these different peaks are. Okay. All right. So let me actually show you the problem that we're going to do with this spectra. So it asks us simply, based on the spectrum, to write the ground state electron configuration of the element, and then to also identify the element. Okay. I'm actually going to do this just on this piece of paper. Okay, so I'll do part A over here. Okay, so the first thing we have to do is write the ground state electron configuration. All right, so going from left to right, it's this decreasing binding energy, right? And if you were watching the first video, what you saw was that basically these just go in order of the orbitals. Okay, so this is going to be my 1s orbital. This would be my 2s orbital, 2p, 3s, 3p, and then the 4s orbital here. So that part's not too hard. The tricky part is being able to assign the number of electrons to these different orbitals. And that's where you have to pay attention to the height of the peaks. Okay. It's pretty safe to assume that for these photoelectron spectra, that the orbitals on the left side of the graph are full. Okay, You can sort of confirm that by looking at each of the different types of orbitals. So I have a 1s orbital, 2s orbital, 3s orbital. They're all the same height, right? Not this one. Okay, I'll talk about that in just a minute. But the 1s, 2s, 3s orbital, all the same height. We know that s orbitals can only hold 2 electrons, so it's pretty safe to say that those all contain 2 electrons. What that's ultimately going to mean for this guy over here, since its height is less than that of the others, there's probably only 1 electron in that 4s orbital. And we can apply a similar concept to the p orbitals. We have these, the 2p and the 3p orbital, both the same height. Once again, if we have an electron here, safe to assume that the orbitals to the left are full, and so we can assign 6 electrons to those. We also can know that those orbitals are full because the question asks us to write the ground state electron configuration. Okay, so it's not the excited state, right? If it was the excited state, then maybe some of these orbitals on the left wouldn't be full, but it tells us explicitly it's the ground state. Okay, so I have my electron configuration right here. I'm just going to write it in this order. 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Okay, now it doesn't say anything about this being an ion, so we're just going to go ahead and assume that this is a neutral atom, and under that assumption, the number of electrons would be equal to the number of protons, and so we can figure out which element this is. There's a total of, let's see, 4, 10, 12, 18, 19 electrons here. Okay, so assuming atom is neutral, this would be the element potassium. Okay, symbol K. All right, so pretty simple. All right, there are some problems that you'll be doing for me that ask you to do a very similar thing to this. This is just called like interpreting photoelectron spectroscopy data. And then there's some questions actually before that that talk a little bit about just ionization energy in general. That's where you're going to have to sort of apply Coulomb's law. In Friday's class, like I mentioned a few times before, Mr. Akampora is going to be with us, and he's going to be doing some work with us on Coulomb's law. So hopefully that activity accompanied by his videos that he produced will help you out a little bit in that arena. Okay, that's it. Thanks for watching, and I'll see you guys on Friday.